unfortunately, some guys latch on to this and say, okay, so if that's true, all right, so we're cool there, right? Okay, so if that's true, then anything like that is easy. So this is going to be, yay. All right, you don't be so condescending. So. It's easy. No, that's just crap. If you took this guy's derivative, what do you get?
1 over 2. 1 over whatever.
Times. Is that there? No, and you can't put it there. If it's not there, you can't put it there unless it's a number. Constants I can put there if I need them there all day long. Take them out, put them in, whatever I want to do. But functional pieces, x pieces, if they're not there, I'm screwed. It doesn't work that way. So thankfully, this is actually based on one of the arc trig functions, right? And those are some of the ones I said you didn't have to memorize. If you haven't noticed yet, actually maybe it's in the next section, so that would be a good reason for you not to notice. Well, I think 5.2 they even had this, maybe. No, not quite yet. I guess it is in the next section. On page 398, they got a nice big box full of integrals, antiderivatives, integrals. We know they're the same thing now. So the integral of x squared, 1 over x squared plus 1 would be inverse tangent of x. So it would be related to that. Cool.
I was just confused a little bit with this. How to do it.
But so the larger thing to this is if you think you have the right answer, you got to double check. If you think this is the answer, it can't be because it would have a chain rule piece that's not there. Therefore, that must not be the way to do it. I like it. So the only way that this could become ln is if this is to the first power. Any other power is going to be differently related, right? In fact, this, what would this be? This is not ln. How would I write that so it's easier to look at?
X -2.
Yeah, now I can just use the rule, right? What's the rule say?
Add 1.
Add 1.
Over whatever you want to go. -1.
I like it. So if you try to apply this rule to this, what happens? Add 1 divided by the new, oh shit.
Yeah.
So that's why natural log saves are asked. It says, oh yeah, that rule only works if it's defined. If it's undefined, then it's going to be some kind of natural log. Because when the x is to a first power, then it's related to an ln. When it's not to a first power, like here, or like the one I had earlier, it's not going to be related to ln, right? Unless it has the chain rule piece. So if I said, what's the integral of, what you got, Jeff? So you guys can see this. So what does that kind of reduce to if you forget about that? Isn't that 1 over x? Basically, if you take the 3 out of the way, it doesn't matter. So a good guess would then be this, and sure enough, what's this guy's derivative going to be? 1 over x cubed plus 1 times 3x squared. There you go. It's got the chain. So this piece here is the chain rule piece. So that's why I was trying to get you guys used to looking at it that way before we got into this new stuff. Is thinking about does it have, like we did this one the other day. That is related to the chain rule piece of that kind of thing. Okay.
So if it's a arc function, then you will just check the denominator.
If it's
like arctangent.
Oh, yeah. Then you look at the denominator to see what's going on. Yeah. So remember, I didn't make you memorize the arc trig function derivatives, which means you got to watch for those intervals. Maybe you want to have them sitting next to you. So when you see, so put next to you somewhere the derivative of this is that. So if you see this, when they're asking you to integrate it, then you know it's going to become arctangent. Yeah. Cool. I like it. The more derivatives you have memorized, the more integrals you're able to do immediately. Now in Calc 2, you actually learn a process that will work on this. You don't have to have this memorized. You just do a little substitution thing, and you actually just work out that it comes out to be this. You can kind of like prove this a different way backwards in Calc 2, if you're going to take Calc 2. All right, well, any other questions from homework? We officially made it through 5.3, but 5.4 is 5.3, to be honest. 5.4 is actually 5.3 more fundamentally. So here's what 5.4 is all about. Starts off about indefinite intervals. So remember, what's definite interval? What is that? What does it mean? Good. It's got limits to it. It's got boundaries. It's a well-defined region. All right.
Can't go across that.
Say again?
Can't cross 1. I mean 0. Can't cross 0. You can't.
Well, it depends on the function. I could have a function that's defined everywhere. It's fine. So, I mean, I can't do this. I can't do that. But I can do this all day long.
Okay.
Yeah. So the only reason I can cross 0 for this is because this is not defined at 0. It's not continuous at 0. Okay. Cool. So definite integrals have the limits on them. I like it. Indefinite, I've already been using this notation, to be honest. I've already been using this. All an indefinite integral is just referencing the antiderivative directly. It's not an area because I haven't defined what region I'm curious about. So we've already used this without any limits on it. So we've basically already done this. So for example, if I said... Nope. I have no idea who Dave is. I thought you were just with somebody and you were just bored and want to sit in a classroom.
No,
Sorry,
I'm
buddy.
trying to take a makeup.
Uh-oh. All right. Good luck. All right. Sorry, so say it again.
I know like a Dave on it.
Do I look like a Dave? Yeah.
Negative cosine.
Negative, yeah. Good. Negative cosecant x plus c. So an indefinite integral represents, you're going to love this, a family of functions. So one member of this family is negative cosecant x plus 7. Another member is negative cosecant x plus pi. And so forth. Well, any value of c, what does it change? If I were to graph this and I change c, what changes? Yeah, how far up and down it is. It changes the y-intercept, essentially, but it just changes. So really think about it. If all I know, when I integrate this and get this, what is this related to this then? What would I do to this to get this? How do I check my work after I integrate? What do I do? Take it right. So this guy represents the what of this guy, geometrically. The slope, I love it. So you take a derivative to get this guy, must be the slope of that. So if all I know is the slope of a function, see how I just drew a function? And it's got a certain slope, doesn't it? Everywhere it's got a slope. Do I know where it is if all I know is the slope? No. So that's one reason why this plus c exists, is because it could be sitting anywhere. Up and down, up at a billion, down at negative 18 trillion, at 0, I don't know where it's sitting. All I know from this function is what the slope is. I have no idea what the function values are. So that's why they have to tell me, oh yeah, f of 1 is 6 or something, and then I can figure out what c is. I have to know something about where the function is to figure out what this is in general for that poor little dude. Okay, cool. So that's what they mean. If you're reading in the book and it says a family of functions, that's what it means. It's the c as if I put plus 2 versus plus 1, that's Bobby versus Billy. All members of family, yes.
Once you figure out C for like one equation, does it change?
In a given problem, it won't change. Obviously, you're going to have a whole different problem. So if I told you that f of, what, Jeff? I don't know, Jeff. Pi was 2, can you tell me what c is? In this case, no. Let's make it pi over 2.
Pi over 2.
It's better. Otherwise, it would be undefined. So what's negative cosecant of pi over 2?
Cosecant is 1 over...
Negative 1, good. So
Yes.
cosecant is 1 over sine. Sine of pi over 2 is 1. Negative that is 1. Negative 1 plus c is 2, so c would be 3. So for this problem, it's always that. You can't, that's true for this function. It can't suddenly go, no. It'd have to be a different, like part B, maybe they say, what if we would have told you this?
So when you said C could be like 7 or 9, or it's like that one and that's it. It can't be both. It has to be
Exactly. Yeah, you can't have a function that's like, well, on Tuesdays I'm here, and on Wednesday, no function. You are somewhere, right? Because we normally don't have a piece of a function that is itself undetermined. We just have the x variable that it can change, but the y-intercept can't change.
What about when we're doing the area and it's like everything under that?
Well, see, I'm given a function then. You see what I'm saying? I'm not just given a slope. I'm given where the function is. But if I just tell you f prime, then it could be there, or it could be there, or it could be there. I mean, I don't know where it is. I just know the slope. I know what it looks like. I don't know where it is. That's why this is undefined. I mean, not really undefined, but not a hard number until I figure it out. Somebody got to give me I think of it like a thumbtack. You got to tell me somewhere. It's, oh yeah, here it's there. And they'll go, okay, now let me fit it in. By doing this work, it fits it in so it goes through that thumbtack. Does that make sense? If I only know the shape of it, I know it could be anywhere up and down. Anyway, this solidifies where, if I can figure out what that is. So when they say, so what's the integral of x dx?
X squared over 2.
Good.
Plus z.
So that's a family of functions because it could be this or it could be this. They're all parallel to each other in a way, right? And it's curvy, but they never touch, right? So once I figure out what c is, that'll tell me which one it is. But it's a family. They all have the same derivative because they all have the same slope, but they're not the same function. They have different outputs. Because all I know if I know f prime is the slope. That's all I know. So when you work integration is backwards, I don't have enough information just by itself to know exactly where it is. That's why they have to give me this extra piece. We've already seen this. They give me something else so I can figure out where it is. I like it. Okay. Cool. All right, where are you at? Okay. So really, 5-4 we've done. I think it's not even a new thing. I don't know why they make it sound so amazing. If I knew the rate of change of something, so for example, I know the velocity of something. What do you get when you integrate it? Position. It's amazing. So if you know a rate of change, when you integrate that, you get the amount that it changed by. So if I know velocity, it's the rate of change of position over time. So when I integrate it over a certain amount of time, I'm going to get how far I went. The net displacement, right? Because if I start coming back to myself, then it's going to be smaller, like the negative area. It's going to be smaller and smaller. It's how much displacement. So when I go here, and I go back there, it would come out to be 0. Because I went and came back. I like it. So you got the same kind of issues we did way back when we did that S of t and V of t thing first, where you had to kind of draw it out and see where it turns around. That same kind of thing happens. I like it. Maybe. So the net change theorem sounds really substantial. It's kind of silly. If I know the rate of change of something, when I integrate it, I get the total amount of that thing. The rate of change of position, I integrate it, I get the total change in position. I get how much position change total. I like it. Cool. So let me see if you got freaky homework questions. They got all kinds of definite integrals in here too. Let me see. Oh, all right. Let's talk about this a little bit. See if you guys remember this. Can anybody tell me something about that expression?
So that's piecewise. Like you create a system.
Yeah, you could. Well, you mean piecewise?
Yeah.
Yeah, and that's why I personally dislike the fact that we came up with absolute value symbols. When you learn more math, you realize it's a larger idea that makes sense than other things. But this is kind of hiding the fact that this is two different things. Depending on what? It does two different things depending on what?
Negative or positive.
Exactly, whether it's negative or positive. So what numbers makes this positive? Anything bigger than 1. I love it. And of course 0, what would the absolute value do to it? The same, it would do nothing to it, right? So if x is at least 1, what will the absolute value do to this number?
No.
Nothing. So what would the result be? What would the result be?
X minus 1.
X minus 1. I love it. It does nothing to it if it's positive, right? Well, what if it's x is less than 1? Then what kind of number is this?
Negative.
And what's it going to do to it?
Multiplied by negative.
Multiply by negative 1. So what do you get when you multiply this by negative 1?
Negative x plus 1.
Oh, okay. That was cool.
Right, and let's test it. What if x is negative 3? So this is telling me the absolute value of x minus 1 should equal 1 minus x because it's below 1. So sure enough, the absolute value of negative 3 minus 1 is 1 minus negative 3. It's 4. Well, of course, we just did, first we did what it was going to do. We didn't do it depending on what number. I just said, if you have a number somewhere in this range, this is what it does, or it doesn't do. I like it. So how does that apply? You know, there's a reason I'm talking about this related to integral. And like, what's this shit about? We're doing integrals, and then you're freaking out. So what if I want to integrate from 0 to 2 this? And I'm not going to let you graph it and do triangles, because that's what you could do. Another part of this homework in this chapter, you could graph it, do the triangles, and get their areas. No, I want calculus, pure calculus.
I think in 5.2, there's a similar one, and you separate it.
Yeah, you separate it around what point, of course. We already figured out what point we're going to separate it around. Where does things change? 1. 1 is where things changes. So, below 1... Below 1, what's true? How can I rewrite this below 1? We already told ourselves. Yeah. So this would be from 0 to 1, this would be 1 minus x. From 1 to 2, this would be... So above 1, x minus 1. Stay with me. Do you guys see the need for that? The reason that is, it's a byproduct of the evilness of the absolute value. Like John said, absolute values are actually two different functions. It's just, to me, it's just kind of evil. So you always got to realize, if I want to do something to it, we had a problem earlier this semester with a derivative of an absolute value, and you had to break it out into its two possibilities to show it wasn't differentiable at a certain point. This won't be differentiable at 1, because it's negative slope there, and then it's positive slope. Oh shit, that's got to totally not be differentiable. Yeah.
But it would be two areas, right? Two areas of any of these functions, because they would be the same, right?
Yes, so because I chose to be symmetric around 1. So you got to be careful. If I would have made this 7, you couldn't do that, right? Because this was symmetric around 1, then it will be equal areas. You could double one of these, but if you don't happen to notice that, how would you do this? What's the integral of 1 minus x?
X.
X minus?
X squared over 2.
Yeah. From?
0 to 1.
And we basically already did that, just 1/2 x squared minus x from 1 to 2. We stop there for a second. Why can't I just cancel these out? Yay! It's 0. Because they're evaluated at different, they don't have the same values as each other always, do they? This is for 0 to 1, this is for 1 to 2. So don't get all excited, these are not the same, these aren't the same. This is for values between 0 and 1, this is for, and you can't cancel them. To be honest, like John said, they end up being the same. This is going to be this is going to be the same value as that, so you end up doubling them all. You don't end up canceling them, but you don't have to realize that. You just value it. You just throw a 0 in, that's nice. You throw a 1 in, you get 2 and a half. Here you throw a 2 in, you get 2 minus 2,
0.
and then 1/2 minus 1. So you get 1. Oh snap. So it was double either of them. They ended up being the same because it was symmetric around. See, it becomes 2 equally spaced triangles, doesn't it? So the area of that triangle is 1/2, the area of that triangle is 1/2. That's what it is geometrically. What's up?
How do you get positive 1/2?
Where are we at? Here?
Yeah. 1/2 minus 1 is positive 1/2. Yeah.
Where'd it go? Alright, let me pull it up here.
1/2 minus 1.
Oh, I see what's going on. Alright. Alright. That's my fault. Let me show you what happens. So remember, when you plug a 2 in, minus plug a 1 in. That's my bad. I just did that automatically, but we're kind of new to this. That's where you want to really show yourself exactly what's going on. Now, the problem like this, especially when there's a lot of values to do, you want to show yourself what the hell you're doing. Yeah. So yeah, I agree with you. So this would be 2 minus 2, that's my 0, minus 1/2, minus 1 is negative 1/2, that's why it became positive 1/2. I like it. Big ass. Remember, it's always f of b, big ass f of b, minus, because you've got to subtract the areas to get the area you want. Never forget how we developed what that means. How are you feeling? Okay, Troy, you
I was going to ask why there was a plus at the bottom and a subtraction at the top. Like, why do you add the two sums? But then I remember that you're adding two separate functions, and then you subtract.
Exactly, you subtract. So that second one became minus and negative. Cool, I like it. All right, good. Maybe, all right. Let's see, anything else freaky in this section? I don't think so. Oh, some of the more obscure derivatives. Like, what's the derivative of this? What's that?
3x.
I love it. 3x. ln. Remember, when it's not e, even when it is e, it's that, but ln of e is 1, so it doesn't show up. So, what's this?
It's 1 over whatever the derivative was.
1 over ln 3.
Yeah, it wants to be 3 to the x, but if I took this guy's derivative, there'd be an ln 3 that's not there. I want you really with me. That's the basic idea of this is it's itself. It's just off by a number. So if I took this guy's derivative, there would be an ln 3 that isn't there. So there must be an over ln 3 that would kill it for me. Oh snap. So in general, if I have an integral a to the x dx, what is that?
A to the x over x.
And you can see that there's restrictions on what the base can be, right? Because ln can only handle certain numbers. I like it. So that's an obscure derivative that we don't come up across very much. The same thing for logs. They're sort of the same way, right? For general natural logs, easy. But what's the derivative of log base 3, for example? What's the derivative of ln?
1 over x.
So you just need an adjustment because it's base 3.
Log
Oh.
Do you remember that? No.
No.
Remember, does anybody remember change of base? Not ace of base, change of base. Oh, I suppose so. No. Base on the bottom, base on the bottom. So that you can always do any logarithm, you can change the base to an e or a log 10 if you want to. So really that's what that is. And what's the derivative of this? Well, 1 over ln 3 is just a constant. And what's the derivative of ln x? 1 over friggin' x. Yeah, so that's what that is. So what's the integral of log base 3? Or let me, sorry, that's evil. What's the derivative of?
Thank God.
What's the integral? What do I want to say here? I don't know if they're going to do this to you. Actually, that would be a little evil for right now. They could have done it to you, but they don't do it to you yet. Okay, we'll worry about that when we get to it. Oh. Last thing before we get into the new stuff. Okay. So there's no quotient rule for integration. There isn't. But again, the central theme of the semester seems to have been simplify first, right? So what can you do?
2 cosine x. Because it's,
Yeah, because what's sine 2x?
2 sine x cosine x.
And so you guys like, sure.
Bye, John.
You gotta know. Now you see why. You gotta know those trig identities. I mean, that's why you went through that in pre-calc. That's why it's called pre-calc. It's getting you ready for calc. So you gotta know these so if they show up, you can use them immediately as you need them. So, question, will this be on the test? Hell freaking yeah.
Sine x, sine x.
So now this will be integral 2 cosine x.
So it's going to be 2 sine x.
Beautiful, right? 2 sine x plus c. Now, how do I know? Now, real quick. I saw this on the homework. So, why is it not negative, number 1? Because the derivative of sine is
Cosine.
cosine. No problem. It's only when I integrate sine I have to put negative cosine. Because their cosine is not sine, it's negative sine. Oh, shit. So be careful about that. Secondly, how do I know this did not come from cosine x squared? You see why somebody would believe that? They put the 2 back up. Number 1, cosine doesn't have that rule in general. It's polynomial stuff.
And
More importantly, this would have a chain rule. Is it there? No. Right? So that's why it's not. If I did have this, what's its derivative? What's the derivative of this? 2 cosine x.
negative sine.
Negative sine x. I like it.
So it's
Which is negative 2.
sine 2x.
I'm sorry. Negative sine 2x. Gas. So if I have a piece of it that looks like the derivative of another piece of it, that's when I can integrate it directly back. When I have like a chain rule looking thing, when I can pull that 2 back up. I can't do it here because it doesn't have the chain rule piece in there. That 2 must just be a number, a coefficient. Ooh, so I just focus on the integral of the antiderivative of cosine. Okay, maybe. Okay, so today, the main thing for today is U substitution. So, I want to remind you guys, help me out here. Alright. So what if I had some U that was actually itself a function of x? So U could be square root of x, U could be sine of x, U could be anything. Some function of x. And then I said, take the derivative of okay, good start. Times u prime. I love it. Kick ass, right? And what's a better way? Let me say it like this. So that's the idea. That's chain rule directly. Now let's bring in a slightly different format that we've used before. So what if I had sine u, and I have the derivative of d sine u. The derivative of sine would be cosine u times du. Because then I can do like du on the bottom like that, and that would go away. Cosine u times du. I love it. Du dx. There it is. So I can take those dx's away. Let me stop there for a second. So that's really what I'm saying here. D by dx is sine u. Is cosine u times du dx. That's the same thing I've said up there. Let me stop there for a second. So that means then that d sine u is cosine u du. Okay, that's crazy. Crazy. So then what's the, get in there, u.
A.
The integral of cosine u du would then be what?
Sine.
Sine u, I love it. So this is kind of weird looking, right? Let me ask you this. A little side note here. This is going to be a little weird. What's integral of dx?
X.
Yeah, because what's understood to be in there?
1.
1. So this is x plus c, right? So we need a plus c when we actually do that. What's the integral dm?
M.
That's crazy. What's the integral d tangent theta? Tangent theta plus c. I love it. I love it. Because you're undoing the derivative of that. You're undoing the derivative of x, so of course you get x. You undo the derivative of m, of course you get m. Undo the derivative of tangent theta, of course you get tangent theta. So here, that would be undoing the derivative of sine u. So of course you get sine u. And over here, what is the integral of cosine u du? Sine u, okay. So I mean, that's, this way of writing this is correct. It actually keeps it, it maintains the equality. It keeps it true. So what can I do with this? So what if, so looking at this. So this is what we have here now. We've got that this is that. We know that's true. Plus c. So what if